All right, now let's take a look at building series solutions about ordinary points. So in this section, we're going to start with a definition that will distinguish between two types of points on a homogeneous linear ODE. For our purposes, we're going to stick with second degree equations, and we will be building series solutions to ODEs around these two different kinds of points. So let x be some number, which we'll call x naught. Let's have that be a point. And let's have y double prime plus pxy prime plus qxy equals 0. Let's have that be a second order. And for now, we're going to stick to second order only. Linear homogeneous ODE. And here we're even nice enough to put it in standard form. If it's not in standard form, go ahead and divide by whatever the lead coefficient function is to get yourself into standard form. Now, if both p of x and q of x, these two coefficient functions here, if these two are analytic at x equal x naught, which remember analytic simply for our purposes means you can create a power series around that point using that point as your center, then we say that x naught is an ordinary point. Of our ODE. All right, but what if either P or Q are not analytic? Well, then you don't have an ordinary point, and the opposite of an ordinary point is called a singular point. If x equal x naught is not an ordinary point, then it is a singular point. Now, there are actually different categories of singular point. We'll talk about that later. For now, it's just ordinary versus singular. So one thing to recall is that a function is not analytic automatically if there's a discontinuity at some value, or if that value is just straight up not in the domain of your function. So let's go ahead and take a look at an example here. And let's say we have y double prime plus e to the x over x squared minus 1. Oops, there we go. Y prime minus the hyperbolic cosine of x over x squared minus 1 y equals 0. Here, it's already in standard form. It looks like the x squared minus 1 was the function that you would have had as a coefficient here, but they're nice enough to divide it for you. That's that way you don't forget. And the question here is to, let's check to see if this has any singular points. So here, determine all the singular points. Okay. All right, so we're not going into this blindly. We're not going into this with no previous experience. We know about power series in the context of Taylor series as we see those in Cal 2. And hopefully you remember that the exponential function is one of the basic examples of something that has a Taylor series around any point, or a Maclaurin series around any point. Oh, sorry, around 0 specifically. Likewise, cosh, sinh, sine, and cosine, all of these are analytic. And in fact, you go out of your way to find the power series for these in Cal 2. Now, the denominators, you're like, oh, I don't remember ever making a power series for a polynomial. Well, that's because you don't need to. Well, why is that? Because it's already basically a power series anyway. Because remember, a power series is essentially a polynomial, but whereas normal polynomials usually end at a highest power, power 2, power 3, power 4, a power series keeps on going with its power increasing to infinity. And you say, well, if that goes on to infinity, then this can't be a power series. Right? It's missing x to the third, x to the fourth, x to the fifth, x to the hundredth, x to the millionth. Okay, fine. If you really feel like having those, this is -1 plus x squared plus 0x to the third plus 0x to the fourth plus 0x to the fifth plus 0x to the sixth plus 0x to the seventh and so forth and so on. And there you go. That's a power series. So trivially, every polynomial is in fact a power series. Every polynomial is analytic. Okay, so these we learn about in Cal 2, and these, just by the definition of a power series, we can classify them trivially as a power series. So each component, and of course here the coefficient is 1, but that doesn't matter. We just care about P and Q. Here, each component is analytic. I can create a power series around this piece, this piece, this piece, or this piece. But that's each individual piece. P is not made up of two different pieces. It's actually one big fraction. Same thing for Q. Oh, and if you ever have a function that is not continuous somewhere, well, then you cannot create a power series around that point. Likewise, if you have an interval around a point where your function is not defined, then you can't create a power series around that point either, because there is nothing around that point. So here we note, oh, each piece might be continuous, but the denominator can make, if the denominator is 0, can make one or both of these, well, okay, I guess both because they have the same denominator, can make both of these discontinuous and therefore not analytic. So here really what we're looking at is x squared minus 1 equals to 0. Okay, well that's what, x plus 1, x minus 1 equals 0. Or in other words, x equals minus 1 and x equals plus 1. So these two are the only values at which my P and my Q are going to be discontinuous, and therefore the only place where they're going to be analytic. Where they're not going to be analytic. And so we can say the ODE, this equation, is, has all the numbers except for those two as ordinary points. So from negative infinity to negative 1, union with negative 1 to 1, union with 1 to infinity, has all of this as ordinary points. The singular points are everything else, literally just those two, I guess, yeah? On the other hand, you have x equals negative 1 and x equals positive 1 as singular points. In general, that's a good way to consider these functions. Consider each piece. Okay, each one of these is nice. It's something that I know the power series of. It's a polynomial. And then consider the whole thing and check to make sure there's no discontinuities, namely wherever you're dividing by 0 or wherever you have a negative inside of a logarithm or something like that, which is disallowed algebraically. Now, one thing that you should note is that these singular points here, 1 and negative 1, these are real values. That's not necessarily true. So in our next example, it's the same kind of question. Let's find all the singular points. Find all singular points. Oh, determine, whatever. Singular points of, and we'll say, let's do this one. We'll do x to the power 6 minus 1 times y double prime plus x y prime plus y equals to 0, like that. Okay, now be mindful of the fact that even though this is an ODE, in fact it's a Cauchy-Euler equation, since the coefficients are polynomials, it's not in standard form. And for our definition, we start with things in standard form. Okay, so let's go and divide this first. Before they were nice enough to do it for us, but now we do it ourselves. And so our P and our Q are these two rational functions. Okay, so just as before, let's consider each piece separately. Well, x is polynomial, and polynomials are always analytic. and that's a polynomial, and so is that, because they're the same, and so those are analytic. And 1 is trivially a polynomial, right? It's a polynomial of degree 0, but in any event, it is a polynomial, and therefore it's analytic. So each of these pieces is analytic. But now let's see what happens as we put them together. Oh, well, as we put them together, we end up with rational expressions, and so a rational expression will be undefined. It'll have a discontinuity, and therefore will not be analytic if we have a denominator of 0. Okay, so similar to the previous one. So if I do x to the 6 minus 1 equals to 0, let's see what I get there. Okay. Well, x to the 6 minus 1 is the difference of squares, because after all, that's like saying x to the 3rd squared minus 1 squared. And I know that I can factor the difference of squares by saying the x to the 3rd plus 1, and then x to the 3rd minus 1 equals to 0. Oh, but I can factor a sum or difference of cubes as well. Sums, differences of squares is one that you see all the time since algebra. Sums and differences of cubes you might not have seen since algebra. It's not something that comes up very, very often. So if you don't remember the formula for that, I don't blame you, but it is something we need here. So let's remind ourselves of that. This one would factor as x minus 1. And then this would be x squared plus x plus 1. In general, if you have, let's put this to the side, if you have x cubed plus, let's say y cubed, for example, sum of cubes, this one will be x minus y times x squared plus x times y plus, plus y squared, like that. Oh, no, it won't. That last one should be a minus. There we go. That last one should be a minus. No, that's not right. Let's see. Oh, yes. I'm thinking of difference of cubes. For a sum of cubes, yeah, we change this one to be a plus, and this one in the middle should be a minus. Oh, it's been a long time since algebra for me as well. So here, this one should be a plus, and this one should be a minus. There we go. So that's the formula for the factoring of the sum of cubes. For the difference of cubes, that's the one where we start off with x minus y, and then this one is x squared plus xy plus y squared, like this. And so here our x is x and our y is 1, so that one factors as x minus 1 times x squared plus x plus 1, like that. And yes, of course, that's equal to 0 as well. It's the same equation. Okay, well, x plus 1 equals to 0. That's going to give me x equals minus 1. Over here, I get x minus 1 equals to 0. That gives me x equals plus 1. But now these are quadratics. And I'm not seeing how to factor those. But we know that we can always find when a quadratic is equal to 0 using the good old quadratic formula. So here x is going to equal to negative b, which is a negative 1. So negative of a negative 1, plus or minus the square root of negative 1 squared, minus 4 times 1 times 1 for AC, all over double the value of a, double 1. So here that gives me a positive 1, plus or minus the root of 1 minus 4, that'll be 3, negative 3, over 2. But remember that if you take the square root of a negative, that's an imaginary value. So here I get x equals 1 plus or minus I root 3 over 2. And likewise here, we could do the quadratic formula. We could use the quadratic formula. That gives me negative of 1 plus or minus the square root of 1 squared minus 4 times 1 times 1 all over double a, double 1. And so that gives me negative 1 plus or minus the root of 1 minus 4, negative 3, all over 2. And you get something that's almost identical to this one, except that the first expression here, the first number is a negative. So we get negative 1 plus or minus I root 3 over 2. So this gives us 6 results. We get x equals positive 1, x equals negative 1. Here, x is 1 plus I root 3 over 2, but also 1 minus I root 3 over 2. That's 2 solutions there. And then here we've got -1 plus I root 3 over 2, or -1 minus I root 3 over 2. So here we have 6 different values, and these 6 values are our singular points. So we have 6 singular points here. Which means everything else that everything other than these 6 singular points would be an ordinary point. Oh, so we can accept complex numbers here? Yes, we can. And in fact, our next theorem here highlights that a little bit more explicitly. You say, wait, are we about to have to start doing calculus with complex numbers? No, nothing quite that sinister yet. There is a course that would, there are courses that involve calculus with complex numbers, but complex analysis is not something we're prepared to do yet. We are going to have a theorem here that highlights the possibility of a complex value, but it only does so in kind of a passing way. The fact that you know that it's complex is sufficient. So here let x equal x naught. Let's have that be an ordinary point. Of y double prime, and again for now, for this chapter, we're sticking entirely to second order things, plus a, what do we call them? P, we call them P before, right? Pxy prime plus qxy equals to 0. Okay, so let's have an ordinary point of this kind of equation. Then there exists two linearly independent solutions to this ODE. That take the form of power series that are centered around that ordinary point. That are power series. There's two different power series, but they're both going to be centered at this point. Note that they're not specifying any specific ordinary point. They're saying just take an ordinary point. So if this equation has all of these as ordinary points, well, then I can pick any one I want. I could say, I'm going to make a series solution that's got centers at 2. Or I'm going to make 2 of them that have centers at -5. Or I'm going to make a couple of them that have a center around 0.3. It doesn't matter. As long as it's an ordinary point, it doesn't matter which one. Okay? So there exist two linearly independent solutions to this ODE that take the form of a power series. Both of them take the form of a power series centered at that x. What's more, a power series solution converges that's a terrible looking S, there we go, converges, slightly better looking, at least. Now this is the minimum, it might actually converge beyond this, but it converges at least on some interval absolute value x minus x naught less than r, where r is the distance from our center x naught to the nearest singular point. So from your ordinary point, find the nearest singular point and measure how far that is to the nearest singular point. Which is possibly complex. So these ordinary points, we're going to consider them to be real numbers at all times. However, the singular points, we accept the possibility they may be complex. And from there, we can compute the distance along the complex plane. So for example, Right. Okay. So, for example, let's find the minimum radius of convergence. Because again, this theorem doesn't say that it has to be the interval. It just means this is the smallest possible one. Maybe you converge beyond that, but bare minimum, find the minimum radius of convergence. Find the minimum radius of convergence of a series solution, whatever that series solution might be, a series solution of x squared plus x plus 1, y double prime, plus x squared y prime, minus 2y equals to 0. All right, so we know our p of x. That's going to be x squared over this. And we know our q of x. That's going to be negative 2 over this, because again, we need to divide by this since we need things to be in the standard form. Everything here, numerators and denominators, are all polynomials, so they're by default all going to be analytic. So the only possibility that makes these not analytic is if the denominator is 0, forcing us to have a discontinuity, and so we have to check for that. Okay, so we need to check x squared plus x plus 1 equals to 0, which again, that's the quadratic formula. Negative 1 plus or minus the root of 1 squared minus 4 times 1 times 1 all over double 1, which is negative 1 plus or minus, that's the square root of negative 3, which is I root 3. You take the square root of a negative, that's imaginary, over 2. Right. So here we find our two singular points. So what we want to do is we want to find the minimum radius of convergence of a series solution of this, oops, I forgot something, that is about, or you can say centered at, x equals negative 3. Okay? Now, this next part of the explanation can be done entirely algebraically, but honestly, it's a lot easier to explain it for me, and is probably easier to be understood by you if I just sketch this. It might have been a while since you saw complex numbers last, maybe high school algebra, but remember that complex numbers can be thought of as points on a plane called the complex plane. Basically, consider this horizontal axis as being real numbers, and consider this vertical axis as being imaginary numbers. Okay, so here, the real part is going to be negative half. So that's how far you're going in the real number direction. Okay, I guess I'm going to the left since that's negative. And then in the imaginary direction, I'm either going plus or minus. Okay, so I'll write it as two separate points. One of them is negative half in the real direction and root 3 over 2 in the imaginary direction. The other one has the same real number, but then the opposite imaginary number. So you can think of, instead of a number line, now I have a number plane, where the real part is given on my horizontal axis, my imaginary part is given on my vertical axis. So this is what, negative 1/2 and then up root 3 over 2. I'm not going to take the time to measure it perfectly, or in fact, I'm not going to measure it at all. I'm not going to put any tick marks or anything, but just more or less, I'm going to the left along the real numbers and up along the imaginary numbers. I'm up here somewhere. For the other point, for my other singular point, I'm going to go to the left and then down. Okay, so left and then down. Okay, so these are my two singular points. Now, I know that I went to the left 1/2. So this right here would be 1/2. So then I want to find the minimum radius of convergence for a series solution centered around negative 3. Okay, well, negative 3 is back here somewhere. It's actually on the real numbers, and it's back here. So now, these are the only two singular points. They're the only two places where my function is not analytic because it has a discontinuity. Those are the only discontinuities I could find. So the idea is, now I want to find the distance, the closest one, to this point? Well, just from the image, I can tell that they're equidistant, right? From here to here or from here to here is the same amount because I'm going the same amount to the right. Here I'm going up some amount. Here I'm going down, but by the same amount. So it really doesn't matter which one I choose. They both have the same distance regardless of the direction. So if I pick either one of these, that'll give me my distance. Okay, but then how do I find that distance? Well, again, we're back to high school algebra. This is a point. Negative 3, comma 0. I'm going to choose this top one, although the bottom one would work too. This is another point, negative half, comma root 3 over 2. And we have a distance formula. The distance formula between any 2 points on a plane, it's not the xy plane, now it's the complex plane, whatever, it's a plane, is going to be the square root of the sum of the squares of, you're going to take the difference in the x values, so negative 3 minus a negative half, and then the difference in the y values. So I'm going to do root 3 over 2 minus 0. You might notice, wait, you flip those. Whatever, I'm going to square it, so the sign will go away anyway. The plus or minus will go away anyway. So here that's negative 3 plus a half. That's what? That's 5 halves. And when I square 5 halves, I get 25 fourths. Here, subtracting 0 doesn't do anything, so I'll just square the root 3 over 2, giving me 3 over 4 under square root. This is going to give me the root of 28 over 4, and 28 over 4 is, what, 7? So I'm going to get root 7. So whenever I create these series solutions, which I haven't done yet, but if I ever were to create one or more, I'm guaranteed 2 of them, but if I were to create one or both, I could guarantee that I would get at least a radius of convergence of root 7. Now, it might be more than that, right? It might be an infinite radius of convergence, but this is the minimum, guaranteed by that theorem. You say, well, are they always going to be complex? No, but if they're not complex, we don't even have to go that far. If they're not complex, just subtract. Right? If this had been a real singular point at just negative half, well, then I would just say negative 3 minus negative a half, and there you go. There's your distance. You only really need to get slightly more complicated if you have a complex singular point. But if it's a real singular point, just subtract. All right, so now that we have some guarantee that we can find a series solution, in fact, 2 series solutions, and now that we have some guarantee that it will converge, at least for some interval, right? Now let's actually take a look at finding what these series solutions look like. All right, so we're going to have, let's say I have an example here. You know an equation is important when it has a name attached to it, right? Here, this is what's called Airy's equation. And when we're done, we will have a result that is what we refer to as a non-standard function. That is to say, that function will not fall into any category that you have learned in algebra, trig, pre-cal, cal 1, or cal 2. It's something that's beyond that. So it's what's called a non-elementary function. And for the most part, non-elementary functions are defined using power series. So this right here is called Airy's equation. And when we're done, the answer that we'll get is what's called an Airy's function. Okay, well, what is the Airy's function? Well, that's a solution to the Airy's equation. So let's go ahead and find that solution. So let's go ahead and solve this. One thing to note here is that there are no singular points. Okay, so note, here our P of x is equal to whatever's in front of your y prime, which we don't have one, and our Q of x is whatever's in front of our y, which is a negative x. Okay, well, both of those are polynomials. Not technically, right? They are polynomials, which means they're analytic. Oh, okay, so P and Q are always analytic no matter what. So here these are always analytic because they're polynomials. And because they're always analytic, there are no singular points. Which means we can find a solution around any point we like because all points are ordinary. And because the nearest singular point is infinitely far away, since there isn't one, then you will be guaranteed whatever solutions you find, you'll be able to, you're guaranteed an infinite radius of convergence. So a solution around any ordinary point has an infinite radius of convergence, because the nearest singular point is infinitely far away. I mean, there isn't one, so you'll never reach one. So trivially, it's infinitely far away. So whatever we get, it will converge for all real numbers, which is always nice. Okay, so in order to do this, first of all, we're going to pick a center. Again, you can pick literally any point. Since there are no singular points, everything's ordinary. But given that we have the choice, we choose 0. 0 is a very common choice for a center because it does simplify some of our arithmetic. And since you have an infinite radius of convergence anyway, it'll cover all real numbers anyway. Okay, so here we go. We're going to go ahead and pick. We pick the ordinary point x equals 0 as our center. Okay, so here we go. We're going to build a solution to this equation, and that solution will be a series solution. That is to say, it will be a power series. So we begin with that. We're going to begin with the most generic power series possible, and that is the sum, as n goes from 0 to infinity, of c sub n. So completely generic. We have no idea what these are. They're just, right now we're just saying it's a sum of numbers. That's about as generic as you can get for a power series, times x to the power n. And here, normally we would have x minus x naught to the power n, but since we chose x naught to be 0, okay, so then that's x minus 0. That's going to be a pretty common choice. This will be x to the n, even though it can be x minus, even though in general it's x minus x naught to the n, because our x naught we will often choose to be 0. Usually this part will disappear and you'll just be left with x to the n. Okay. All right, so that is what we know our solution is going to look like. Just the most generic possible thing we know. It's a power series, which you know nothing about. Okay, well, this equation goes up to a second derivative. So let's go ahead and find the second derivative of this power series. Okay, well, let's see. That's going to be the sum. N goes from 0 to infinity. If I take the derivative, I'm just using the power rule. Take your n, bring it down, minus 1. The c sub n is going to stay the way it is. You're just going to bring your n down, x to the n minus 1. One thing to notice is that when you bring your n down like that, if you plug in n equals to 0, you get c0 times 0 times, times 0. That doesn't do anything. So although you can start with n equals to 0, it's redundant because you're just saying your first term is zeros, so why would I even bother saying it? Okay, well, what if I don't, well, okay, so then I guess I don't start at 0. Let's start up with the next one. Let's start at 1. Well, that would then be c sub 1 times x to the 0. Oh, but x to the 0 is equal to 1, and that's okay. It's not 0. Okay, so n equals 1 is the first index that gives us something that's not 0. So let's start counting at 1. Again, it's not wrong to start counting at 0, but it's also redundant. Y double prime, we're going to take the sum. We're going to take the n minus 1, bring that down. So c sub n times n minus 1, x to the n minus 2. You bring it down, subtract 1 more from the power. And now notice that if I start at 1, that's going to be c sub 1 times 0. And again, the whole thing's 0, so don't start at 1. Let's start at 2, because that would give you c sub 2 times 1. Okay, yeah, that's not 0. Okay, so 2 is the first number that doesn't give you a 0 here. If you plug in 0, you get 0. If you plug in 1, you get 0. So let's start at 2. So if this y is our solution, then this is what its second derivative will look like. And so those two would satisfy this equation. Okay, so let's make sure they satisfy that equation by plugging them in and setting it equal to 0. So this gives us, our equation has now become, instead of y double prime, we've got sum, n goes from 2 to infinity, c sub n times n minus 1, x to the n minus 2, minus x times, and now my y is the sum as n goes from 0 to infinity of c sub n x to the n. That's just y double prime minus xy, and that's going to equal to 0. Okay? So now we have to find c sub n's that make this equation true. All right, so let's see. Well, we've got two series. That makes things even harder than they need to be. I wish I just had one series. Okay, so let's combine. Oh, but in order to combine, I need to make sure make sure all terms are like. I can only combine like terms. Well, are these not like terms? Well, let's see. If I plug in n is equal to 2, which is the first number I'm allowed to plug in here and get something that's not 0, I would get x to the power 0. Okay, so this is going to be x to the power 0, and then x to the power 1, power 2, power 3, 4, 5, on and on and on. So from 0 on up. Over here, you say, oh, well, if I plug in this, that also gives me 0. Well, not so fast, because this whole thing is being multiplied by an x. And remember that when you multiply two things that have the same base, you can add their powers. This is a power of 1, and this has a power of n. So this actually becomes the sum n goes from 2 to infinity, c sub n times n minus 1, x to the n minus 2, which again, that'll start at power 0. But now this will be the sum as n goes from 0 to infinity, c sub n x to the n plus 1. And that'll start counting at 1. Oh, so then I don't have like terms, because this counts 1, 2, 3, 4, 5. This counts 0, 1, 2, 3, 4, 5. Oh, well, those are mostly the same. It's just this one has that 0th term, that one with the power 0 before all the other ones. Okay, so why don't we just take that one off? Here, what we're going to do is we're going to say, well, if we start at n equals 2, then this starts at power 0. But I don't want it to start at power 0. I want it to start at power 1 like this one does. Okay, so then start counting at 3 instead of 2. Oh, but then what happens to that first term that I don't use? Oh, let's separate it. If I plug in 2, I get c sub 2 times 2 times 1. All right, 2 times 1 is 2. And then that 2 times c sub 2 is just going to be 2c2. X to the 2 minus 2, well, that's just 0. So all I've done is all of these n's I've replaced with 2's, and that gives me 2c2 times 1. But now, since I've already plugged in 2, my sum can start at 3 now, because I've already plugged in the 2. So that's going to be the sum, as n goes from 3 to infinity, of all the same stuff. I've just started counting in a different place. I'm still counting the same things. So c sub n times n plus 1 x to the n minus 2 minus sum as n goes from 0 to infinity c sub n x to the n plus 1. By taking off that first term, the one that I had when n was equal to 2, now this starts counting at x to the first power, and this starts counting at x to the first power. Okay, so now these are all like terms. Oh, but now my rules don't match, because here these are counting n starting from 0, and these are counting n starting from 3. And neither of those n's are actually the index I want. All right, I want the index to start at 1. Okay, so let's reset our indices. This won't change anything about the problem. It'll just change the labeling. The simplest way to change the labeling is like this. Take whatever power you have, because that's the one I want to focus on. Those are the ones that match, and so that's what I want to focus on. Take whatever power you have here and call it k, or whatever letter you like, but I'll use k. Send it over here. Take whatever power you have, in this case n minus 2, and call it k. These are not different k's. They're the same k, which is important. That's what we want. We want both of these to have the same power, and we want that power to start counting at 1. Okay, by writing k is equal to n minus 2, that's the same as n is k plus 2. And here, k is equal to n plus 1, which is the same as saying n is equal to k minus 1. Now I'm going to use those to rewrite my indices. Let me leave my 2c2 out where it was before, plus the sum. Anywhere I see an n here, I'm going to replace it with k plus 2. So that's not cn anymore. That's c sub k plus 2. That's not n anymore. That's k plus 2. And that's not n plus 1 anymore. Oh, sorry, that wasn't 1 plus 1. That wasn't n plus 1 to begin with. My apologies. That was n minus 1. Okay, that's not n minus 1 anymore. Now that's k plus 2 minus 1. Okay, so I'll just call it k plus 1. X to the, and then the n minus 2, that's your k. Notice that your k starts counting at 1 now. You say, how do I know it starts counting at 1? Well, two possibilities. One, because you remember that the reason we did this is because we were planning ahead. We were trying to change these powers so that whatever index they have is the same for both, and it starts counting where we had before. Before we had n is equal to 0, and that gives us a power of 1. N is equal to 3, and that gives us a power of 1. So once we change our index, it should start at 1. The other way you can do it, if you didn't think about that, is just to say, well, if n is equal to 3 here, plug it in. 3 minus 2, okay, is going to equal to 1. Minus, I've got the sum as, same thing will happen over here, k will equal to 1 for the exact same reason. 0 plus 1 is 1. K goes from 1 to infinity of c sub, now my n is k minus 1, so that's going to be c sub k minus 1, x to the power of, the n plus 1 is a k. Oh, but now, same powers, same index, now they merge. Oop, and all that's equal to 0, just like it was above. So now we get 2c2 plus a single sum from 1 to infinity. Here, x to the power k is a common factor to these, so I can factor it out. And what's left when I factor that out is going to be this minus this. I'll have ck plus 2 times k plus 2 times k plus 1 minus ck minus 1 x to the power k equals to 0. Okay, now, notice that you have an infinite sum, plus one more, whatever. Notice that this infinite sum doesn't have any like terms that can be combined, because we already did that. We already combined every like term that we could. So right here, notice that this doesn't have an x in there at all. It's a constant. Okay, so there are no other constants anywhere in this problem, because notice, I'm going to count k is equal to 1, k is equal to 2, k is equal to 3, k is equal to 4. I will always have x to a power. Minimum, I'll have x to the first, which means there are no other constants anywhere over here. So if I have this constant plus all of this stuff is equal to 0, and none of this stuff is constant, meaning none of it can combine to this, well, the only way for this to be 0 is if it started at 0. All right, if this is 5, I'm never going to have another constant that can cancel out that 5. Okay, so since I knew it to be 0, it better be 0 from the beginning. So right here, I get that 2c2 will equal to 0. Divide both sides by 2. I get c2 is equal to 0. For now, that's seemingly unimportant since it's just a single coefficient, but that actually comes out to be important later. But for now, let's look at this thing. For the same reason, I don't have any like terms to combine. Because when I plug in k is equal to 1, this is the coefficient x to the first. And then that's it. I'll never have another x to the first again. Because the next number I will plug in will make it x to the second. And the one after that will make it x to the third and fourth and fifth. It'll go on forever. It'll never come back to power 1. Once I hit power 2, I'll never get back to power 2. It always goes up forever. Never comes back. Okay, so what? Well, just like this one, since all of these are distinct, none of them are like terms, that means nothing will combine. So if these all add up to 0, it's because each individual one was 0 to begin with. Okay, so then that tells me that each one of these that I'm adding together is equal to 0. Oh, but x is just some variable, right? X can be 4, x can be 900. X is the variable of a function. X can be anything. Okay, so you're saying for the sum to be 0, each piece must be 0. But if each piece must be 0, it can't come from this, because this can be anything. Oh, well then the part that has to be 0 is this part right here. So then this gives me that c sub k plus 2 times k plus 2 times k plus 1 minus c sub k minus 1 is equal to 0. But notice this is a relationship between an earlier coefficient. Remember, that's what these C's are. They're the coefficients of your solution. This is a relationship between the earlier coefficients and the later coefficients. This is called a recursion. You may remember these from pre-cal. A recursion is almost like a function. It's a rule that tells you if I know an earlier version of something, I can use that to find the later version of that same something. Although that is a recursion, recursions are best expressed and best used if you isolate one of the two things that you're looking for, one of your two coefficients. And the one you should isolate is the one that has the bigger index for reasons that you'll see here in just a moment. So here I'm going to add this over this way. So that'll give me ck plus 2 times k plus 2 times k plus 1 is equal to a positive c sub k minus 1. And then I can divide these two away to give me, it's the same recursion, but this is a more convenient way of writing it. It gives me c sub k plus 2 is equal to c sub k minus 1 over k plus 2 times k plus 1. This is a recursion formula. It's a formula that tells me if I know an earlier coefficient, which I know an early one, hey, this does come in to be important. If I know an earlier coefficient, I can find some of the ones that are later. If I know a C1, I can find a C3 or a C4 or something like that. So from just knowing a little bit about the first few coefficients, I can actually find all the rest. So let's try that. Here, there seems to be something about K that's a relationship. That's important in the relationship. Oh, well, sure. K is just the index marker. It's telling you what position you're in. Okay, well, why don't we try just starting with different values of K? And you say, okay, let's start with K is equal to 0. Well, no, we can't do that. Well, why not? Because if I start with K is equal to 0, I start with C sub negative 1. And remember, your coefficients start at 0. You never have any negative indices. You just have 0 as the smallest possible one. Okay, so I guess I can't start at K equals 0. So let's start at K equals 1. Well, let me write my recursion over here as well, so I don't have to flip back and forth. My recursion is C sub K plus 2 equals C sub K minus 1 over K plus 2 times K plus 1. Like that. All right, so let's plug in a few values of, and I also had C2 was equal to 0. That was another bit of information I had. So let's plug in a few values of K. Plugging in 0 is not going to work because I don't have a C sub negative 1. C sub 0 is the smallest. Oh, okay, so let's plug in 1. That way it'll give me C sub 0. So if I have K equals 1, then that's going to give me, well, let's see, if I plug in a 1 here, that's C3. And over here, that's going to be C0 over, well, notice these two are going to match. So if this is a 3 here, this will be a 3 here. And then this one's just 1 less than that. So 3 times 2. Okay, cool. All right, so now let's plug in K is equal to 2. If K is equal to 2, then I'm going to get, well, let's see, 2 plus 2 is 4, so it'll be C4 equals 2 minus 1 is 1, so that'll be C1 over, and then again, these two match, so if that's a 4, that's a 4. And then 1 less than that is a 3. Okay, what if I plug in K is equal to 3? Oh, well, let's see. If I have K is equal to 3, that gives me C sub 5. C sub 5, 3 plus 2 is 5, is equal to C sub 3 minus 1 is 2, so C2 over 5. Those two got to match, just like those, 5 times 4. Oh, but C2 is equal to 0. So this whole thing just equals to 0. Okay, so C2 is 0, and so is C5. Wasn't that nice? Let's try K equals to 4. Okay, well, let's see. If I have 4 plus 2, that'll be C6 equals 4 minus 1 is 3, so that'll be C3 over, and well, again, those two match, so that's going to be 6 and 5. Oh, but notice that C3 itself we already know. So that C3 I can replace with C0 over 3 times 2. And then that C3 is being further divided by a 6 and a 5. Okay, so 6 and 5. So I get C0 over 6 times 5 times 3 times 2. That's almost a factorial, but it's missing a 4, right? 6, 5, 4, 3, 2. It's not quite a factorial. What if I plug in k is equal to 5? Well, 5 plus 2 is 7, so I'll have C7 equals 5 minus 1, that's going to give me C4 over 7 times 6. Oh, but C4 itself was defined earlier. C4 is C1 over 4 times 3. That's your C4. But now that C4 is being further divided by 7 and 6. Okay, so 7 and 6. 7, 6, skip your 5, 4, and 3. What if I plug in k is equal to 6? Okay, well, that's going to give me 6 plus 2 is 8, so that's C8 equals 6 minus 1 is 5, so my number is C5 over 8 times 7. Oh, but C5 was 0. So that whole thing is 0. Oh, so it looks like these are zeros. Oh, so these all depend on C0, these all depend on C1, and these all depend on C2, or in other words, they're all 0. How did you know to organize them into groups of 3, or was that a coincidence? The recursion told me to do that. How? It talks to you? Is it talking to you right now? No. Well, maybe a little. From here to here, how many steps are there in the index? Oh, this is k minus 1, add 1, k, add 1, k plus 1, add 1, k plus 2. Oh, so there's a jump of 3 steps from here to here. Oh, so that means your recursion will give you values 3 at a time. 1, 2, 3, 4, 5, 6, 7, 8, 9, and so forth. So because there's a step, there's 3 steps from here to here, that tells you there'll be 3 groups of solutions that depend on each other. Let's do one more set here. I've already done 1 through 6. Let's do k equals 7. All right, well, that'll be C 7 plus 2, that's 9. So C9 equals, that'll be C6, 7 minus 1 is 6, over 9 times 8. These two match. This one's 1 less. But C6 is itself C0 over 6, 5, 4, 3. C0 over 6, 5 times 4. Oh, sorry, 6, 5, 3, 2. 6, 5, 3, 2. Oh, but now that C6 is being further divided by 9 and 8. So 9 times 8 times 6 times 5 times 3 times 2. Almost a factorial, but it's missing every third one. Oh well. Here, this one's going to be k equals 8. That'll give me C10. Okay, just plugging in 8 into this formula up here. I get C8 over C7 over 10 times 9. Oh, but C7 itself was C1 over 7 times 6 times 4 times 3. But now that C7 there is being further divided by 10 and 9. Okay, so 10 and 9 like that. So C1 over 10 times 9, skip your 8. 7, 6, skip your 5, 4, and 3. And then this one, as if you didn't see it coming, if I said k equals to 9, that's going to give me C11 will equal to C8 over 11 times 10. Oh, but C8 itself is 0, and so the whole thing is 0. So here you notice that it looks like you have 3 groups of solutions. Oh, but one of them ended up being zeros. So I guess this one doesn't count because your solution will just be 0, right? 0 plus 0 plus 0 plus 0. That's right. So really, you only get 2 groups of solutions. Oh, but that's what our theorem promised us. Our theorem promised, where did that paper go? Oh, here we go. That theorem promised that if we build a series solution around an ordinary point, there will exist 2 linearly independent solutions created that are in the form of power series. Oh, but that's exactly what we form. These coefficients form 2 different power series. So let's see how to put this all together. Uh, Notice here that, well, actually, let's not even do that just yet. Let's actually just start writing a solution. So here I get that y is going to equal to. So right now, the way I'm going to write it, it's going to look like I only had one solution. Okay, but let's see. We know that y is equal to the sum as n goes from 0 to infinity of c sub n x to the n. See, how do we know that? Because that was our starting assumption. Our starting assumption is that because our solution will be a series solution, that's what a series looks like. So it's not even really that's not really even an assumption. It's more of a that's what a power series has to look like. Okay, well that's going to be C0 plus C1x plus C2x2 squared plus C3x cubed plus C4x to the fourth plus C5x to the fifth plus dot dot dot. Because that's what that means, right? You're counting your index up, you're counting your power up, and the index and the power match. Power 0, index 0, power 0, index 1, power 1, index 2, power 2, and so forth. Oh, but now I actually know those numbers. Yeah. So y is equal to, well, let's see, C0 was, well, I guess I never found what C0 was. My algorithm never gave me that. The earliest one I found was C3. So I guess C0 is something I just don't know. It's just some number. Okay, well, how do I find that? Well, for now, let's just try this C0. Our algorithm never gave us that. It told us C3 was the very first one I was able to find for my recursion. Okay, well, let's just write C0 for now. And here, same thing. I never got C1 from my recursion. The earliest one I got was C3. Or I guess technically C2 since that was 0, but definitely not C1. Okay, so I guess I don't know what that is either. Okay, let's call it C1 for now. C2 was 0 though. C3, oh, that one I actually do have from my recursion. That was C0 over 3 times 2. I guess let's just say 6. And that's going to be x cubed. Plus, and then what was the next one? C4. C4 was C1 over 4 times 3, which is 12, x to the fourth, plus, and then C5 was 0 again, so that's 0x to the fifth, plus, let's see, what's our next one? We'll do C6, our next one C6, which we could write C6 here, but C6 simplified to be C0 over 6 times 5 is 30 times 3, that's 90 times 2 is 180. So that's C0 over 180 times x to the power 6. Plus, let's see, our next one is what, C7? So that's going to be C1 over 7 times 6 times 4 times 3. Oh, let's see, that's 7, 6, that's 42, and that's 504. That's 504. That was my C7 from right. I moved my paper and I lost it. Where'd it go? Oh, here it is. C7 was C1 over this product. So that's C1 over 504. C1 over 504, x to the 7. And then the next one was C8, which that one turned out to be 0 also. Okay, so plus 0x to the 8th plus dot, dot, dot. So at this point, it looks like I have one solution. And now you think, okay, so now we got to go find the other solution? The theorem said 2 solutions. Nope, they're both right there. It's not an accident we can find C0 and C1, because look what happens. First of all of these are 0, so let's not worry about those. Second of all, there's an infinite number of terms here, but they fall into 2 categories. Some of them have a C1 in their coefficient. Some of them have a C0 in their coefficient. C0, C1. So anything that has a C0, let's lump that together and factor out the C0. This is C0 times 1 plus 1/6 x to the third plus 1 over 180 x to the sixth plus dot, dot, dot. And then let's take all the ones that have a C1 in common and factor out the C1 and group those together, giving me x plus 1/12 x to the fourth plus 1 over 504 x to the 7th plus dot, dot, dot. Oh, so I actually have two separate series that have been added together. Oh, but notice that these two series never overlap in power. These all have powers that are multiples of 3. 3, 6, 9, 12. These all have powers that are multiples of 3 plus one more. Right? 1, 4, 7, and so forth. So these are never going to overlap. They don't they don't have any dependence on each other. Oh, that's called linear independence. So what do we have? We have two linearly independent series that have been multiplied by constants and added together. That's the way a solution to any differential equation has looked for us since chapter 2, since very early on in the course. So right here, although I'm not going to require this to be written in a series notation as a sum. Basically, what this is y is equal to C0 times the sum of something plus C1 times the sum of something, like this. But that's what solutions always look like. Mind you, these series here do not have to be written in sigma notation for our purposes, for our course. Note that actually is just an alternate notation, and I'm going to be perfectly satisfied if you leave them in this form. But do note that if it is something that's relatively simple to create, you might actually consider writing these in the sigma notation anyway. Especially in applications, sometimes it's better to have the form rather than to have it written out this way. But for our purposes, I'll consider this a fully completed answer. But note that it is the type of answer that you've always had. I have a second order differential equation at the very beginning. So I have a second order differential equation. And our answer is going to be two linearly independent solutions, in this case series solutions. And I'm going to take the linear combination of those two linearly independent solutions. C times y1 plus another c times y2, which is what you would expect. Okay. Let's do one more example of this. This does take a bit of time to get used to in many cases, so one other example would probably be a good idea. Let's take a look at, okay, this is a Cauchy-Euler equation. We'll do x squared plus 2 times y double prime minus xy prime plus 4y equals 0. Okay? And the question is, find a series solution of this ODE about, and again, they're asking for the same thing, x equals 0. One thing to note is that this one actually does have imaginary singular points. So here, one thing note, this ODE has singular points. Again, each component is a polynomial, so it's analytic. But in order to put this in standard form, you would divide everything by x squared plus 2. And if you take x squared plus 2 and set it equal to 0, it has imaginary solutions. So this has singular points. Oh, this pen is dying on me. Let's see. Here, let's try this one. There we go. Has singular points. Let's see, what was it? X squared plus 2 equals 0. So subtract the 2 and take a square root. So x equals the square root of 2 I, right? Because, yeah, okay, so it's going to be the square root of negative 2. So I root 2, and x equals negative I root 2. So because this does have singular points, this series solution might be convergent only on some smaller interval. So here note, because these are our singular points, the distance between 0 and either plus or minus I root 2 is the root 2 part. You can see that quite clearly on a graph. Here's positive root 2. Here's negative I root 2. And here's 0. And to get to either of those, you just go either up or down by root 2. So here, this solution has a radius of convergence of at least the square root of 2. It may converge for an interval bigger than that, but at the very least, it will converge within this radius of 0. Okay, so you are guaranteed to have a convergent power series. It's just not guaranteed to converge for all real numbers like the last one was. But with that in mind, we can still build the power series, even though it may be a little more restricted than the last one. All right, so here we go. We'll start off with the same assumption as before, that y is a power series. It's going to be the sum as n from 0 to infinity of c sub n x to the n. Okay. Here we're going to need, again, a second derivative. So we're going to take y prime, and that's going to be the sum, n goes from 0 to infinity, of c sub n. Here you bring down your n, giving you n x to the n minus 1. And then when you take the second derivative, that's going to be the sum as n goes from 0 to infinity of c sub n times n minus 1, because you bring down the n minus 1 as well, x to the n minus 2. However, just like last time, note that although it's not technically wrong to start at 0, it's also really redundant, because if you plug in 0, the first term is 0. It's not until you plug in 1 that you get something that's not 0. So we should probably start at 1. Same thing here. If I plug in 0, I get 0. If I plug in 1, I'll get 0. The first time I get something that's not 0 is when I plug in 2. So I should probably just start at 2. All right. And so now these, I can go ahead and pop into my equation. So this is going to give me x squared plus 2 times y double prime, which is that thing over there, sum n goes from 2 to infinity of c sub n times n minus 1 x to the n minus 2 minus x times the sum, this is our y prime now, from 1 to infinity of c sub n times x to the n minus 1. And then plus 4 times our y, which is the sum n goes from 0 to infinity c sub n x to the n. And that has to equal to 0. Okay, well now we can distribute. Notice that this series is being multiplied by two things right here. So first I can multiply by x squared, and then separately I'll multiply by 2. If I multiply by x squared, I get sum n from 2 to infinity, c sub n times n minus 1 times x to the n. Because if I multiply this times x squared, it's the only thing with an x, so these aren't affected by multiplying by x squared. You multiply variable with variable. Since these have the same base, you would add their powers. And n minus 2 plus 2 is just n. But then separately, I want to multiply by 2. Okay, well then that would be the sum as n goes from 2 to infinity of, well now here, these were both variables, so I combine those. Okay, well now, this is a constant, not a variable. Okay, so then I should probably not combine it with the variable, I should combine it with the other constants. So this would be the sum as n goes from 2 to infinity of 2 times the other coefficients, c sub n times n minus 1 x to the n minus 2. So multiplied by x gives me this, multiplied by 2 gives me this. Minus, and then here, same thing, multiply across, and since these have the same base, x and x, I can add their powers. So this will give me the sum as n goes from 1 to infinity of c sub n times x to the n, because n minus 1 plus 1 is just n. And then plus, and then here I can just multiply the 4 times the cn, giving me, I need a sigma there, plus the sum as n goes from 0 to infinity of 4 c sub n x to the n, and all that has to equal to 0. Okay. Now I have 4 power series, but I really want just 1 power series. Combine everything together. Okay, so then what I need to do is I need to make sure that 1, all of these start at the same value, all these start at the same power, and 2, make sure all my indices match. I'll change the n's into k's, and they all have to start at the same value of k. So let's see where they start now. This starts at power 2. This starts at power 2 minus 2. That starts at power 0. This starts at power 1. And this starts at power 0. Okay, I want them all to start at the same place. This one's the most disadvantaged one, right? It's missing the most terms. This one starts at power 2, so it's missing power 0 and power 1. So I should cut off terms until I make everything match this one. Okay, so this one, one more time, this one starts at power 2. All the rest start earlier. But since I want all of them to match, and I can't add more terms to this, I should strip off terms from these until they also start at power 2. Okay, so I'll take sum as n from 2 to infinity. C sub n times n minus 1 x to the n. We're going to leave that alone for now. That's already starting at 2. Now, currently, this one starts at power 0. Okay, so I should strip off the one where I plug in 0 and strip off the one where I plug in, where I have power 1. Okay, so when I get power 0, that's because I plugged in 2. Okay, well, let's see what happens when I plug in 2. I get 2 times 2 is 4, times 1 is still 4, c sub 2, x to the 0. So right now, all I did was I plugged in n is equal to 2 right here, and I got this. Plus, now let's plug in n is equal to 3. Now I'll get, well, let's see, 3 times 2 is 6, 6 times 2 is 12, times C3. 12C3. And then when I plug in, I've already plugged in 2, now I'm plugging in 3. 3 minus 2, that's a power of 1. Okay, but now I've stripped off the one that has power 0 and the one that has power 1. So from now on, all the rest will have power 2 and higher, which is what I want. I want them to start at power 2. Okay, so now I'm going to have the same rule. It's going to be 2cn times n minus 1 x to the n minus 2. But now I'm not using 2 or 3 because I've already plugged those in. So now I'm starting at n equals 4. Like that. Okay. All right, what about this one? Well, this starts at power 1. I don't want to start power 1. I want to start power 2. Okay, so let's take off one of those. I'll have minus, because of that minus. Let me plug in 1. Well, that'll just be 1c1, and then x to the 1. Oh, but now I've already used up x to the 1, so now everything else will be power 2 or higher, just like this one. Okay, so then I'm saying minus, and again, it's the same minus. The sum as n goes from 1, oh, not 1 anymore. I already used 1. Now I'm starting at 2 to infinity. C sub n times n x to the n. The rule doesn't change, just where I started counting. And then this one starts at 0. Again, I want it to start at 2. Okay, so plus, let's plug in the first 2 of them then. If n is equal to 0, I get 4c0. If n is equal to 1, I get 4c1, x to the first power. And then after that, the next one will be n is equal to 2, and that's what I want. I want the powers to be 2 and higher. So there, I'm going to have the sum. Not starting from 0 anymore. I cut off 0 and 1. Now I'm starting at 2 to infinity, but the rule remains the same. 4c sub n x to the n. And all that's going to equal to 0. Okay? So now, all of these start at power 2. Power 2, power 2, power 2, and power 2. That's the first value that you plug into your index. But now all of them look different. Even though they all start at the right power, this one starts at 2, at 4, at 2. Okay. So let's see here. Oh, well, actually, most of these are pretty good already, aren't they? Because the way you're going to change your index is you're going to take whatever power you have on your x, and you're going to call that k. Oh, but here k is equal to n. Oh, that's the pen that was dying. Here, your k is going to equal to just n, because it's already just n. Like that. And same thing for this one. Because the power on x is n, well, then your k will equal to just n. So nothing's actually changing for these. I don't have to do any computations. I'll replace n's with k's just to make it look consistent, but I'm not actually doing any computation. Same thing for this one. This one's already got a power of just n, so your k will be just your n. So for these three, I don't have to do any computation. I'm literally just swapping out all the n's with k's. Oh, but this one I do have to do a computation on. Because here, since your power is something other than just n, oh, well, now your k is going to equal to what that is, which is n minus 2. Another way of saying that is to say n is equal to k plus 2. Okay, so here we go. This is going to give me the sum as n goes from 2 to infinity of, k goes from 2 to infinity of c, and all of these that are not sigma, I'm going to go ahead and leave those off until the end. So sigma k2 to infinity, c sub k times k minus 1, x to the power k. Again, no modification. I'm just swapping out n's for k's. This one is going to require a modification because, well, I've already got the right sigma here. Sigma from 2 to infinity, that's okay. But now the rest of this is going to change. It's going to be 2. My n is replaced by a k plus 2. So that's c k plus 2. That n is replaced by a k plus 2. And that n is replaced by a k plus 2 minus 1 is k plus 1. Times x to the, well, now that power becomes a k. Now minus, and then again, all these n's just get replaced with k's, so that'll be c sub k times k x to the power k. And then plus, and then same thing for this one, it'll just be 4ck x to the k. 4ck x to the k. But I'm not done. I still have all these other terms here, so let's go ahead and put those together. Well, 2 of these combine, right? So let's see, I've got C3s, there's only one of those, so it'll be plus 12C3X. And then C2, I've got plus 4C2 just by itself. Oh, that's actually not the best way to combine it, is it? I shouldn't be combining based off of their coefficient, C1 or C2 or C3. I should be combining off of their order. So let's try that a different way. So here, this is a constant, and this is a constant because they don't have any x's, so let's combine those. So it'll be plus, and I'll just put a parenthesis around that. That'll be 4c2 plus 4c0. Combine the two constants. And then I've got 3 linear factors, x, x, and x there. So that'll be plus, and then the coefficients on that are going to be 12c3. And then I've got minus c1, but then plus 4c1. Okay, so 4c1 minus c1 would be 3c1 times x. Okay, so I've gone ahead and merged all of these sigmas together into one big one here. And then these ones that were stripped off from the main parts were grouped together as the 2 constants and the 3 linear expressions. But then those 3 linear expressions themselves condensed a little bit down to be 2 linear expressions. Okay? And all of that still has to equal to 0. But now looking at this, I notice that I have a x to the k as a common factor to all of these terms. So I can factor that out. I can write this as the sum, as k goes from 2 to infinity, of the x to the k will factor out, so let me just add all the other stuff. Let's see, all this other stuff, these are all in terms of c sub k. I could actually combine those, can't I? So let's see. Let's do this off to the side. Just get a separate sheet of paper here and just do that off to the side. Let's see. So I've got 4ck minus kck. Okay. So I've got, and then over here I've got plus k times k minus 1 ck. So it looks like ck is a common factor for all 3 of these. This one, this one, and this one. So I'll get ck, common factor. Here I'm going to get k times k minus 1, which is going to be k squared minus k. And then for this one, I have another minus k. And then for this one, I've got a plus 4. And then those two combine to give me ck times k squared minus 2k plus 4. Looks like that. So that's going to give me, if I combine this one, and this one, the three that have arrows, I'm going to take ck times k squared minus 2k plus 4. Like that. And then this one doesn't have a ck, so I'm just going to write it down the way it is. So plus, and here I'm going to just keep the coefficients separate for now. I may regret that. I may end up having to multiply these later, but for now I'm going to keep them separate. And I'm going to say ck plus 2 times 2 times k plus 2 times k plus 1. All right? And then all of these had an x to the power k. So the whole thing, x to the power k. So these three with arrows came together here. This one just came on down. And then all four of them had an x to the k, which I brought to the outside. Plus, and I'm just going to copy this stuff down here, 4c2 plus 4c0 plus 12c3 plus 3c1x is all equal to 0. And that's condensed it down as much as it's going to go. But now, just like in the last example, we can tell, oh, well, this is constant. There are no other constants anywhere in here. This is linear, power 1. And then here, this will be power 2, and then 3, 4, 5, 6. There are no more like terms. We did a good job of combining everything we could. But since there are no like terms, then everything has to equal to 0 on its own. Because if you have an infinite number of terms, but none of them can combine, and they all add up to 0, well, then that means each individual one must have been 0 in the first place. So here, these two give me a nice small system of equations. I get 4c2 plus 4c0. That's got to equal to 0. And then the coefficient of the x, that must also equal to 0. I have 12c3 plus 3c1. That's also got to equal to 0. Which, at first glance, you might think, oh, I'm in trouble. Because here you're like, I've got two equations and 4 unknowns. How am I going to figure that out? Well, you're not. At least not in its entirety. What you're going to do is the following. You're going to say, okay, let me solve for C2. On the bottom one, let me solve for C3. Wait, why am I solving for those? Because just like in the last example, we're not going to get rid of all of our coefficients. We're going to be left with a C0 and a C1. Okay, but how do you know you're going to be left with C0 and C1 specifically? Because of our theorem. Because of the theorem of this chapter that says that we're going to, guaranteed, end up with two separate series solutions that are going to be linearly independent. We're going to end up with, there exist two linearly independent power series solutions. And because there are two linearly independent power solutions, in the end I'll be able to get some power series times C0 plus some power series times C1, like in the last one. So here the C0 and C1 are going to be what define everything else. So here let me solve for C2 in terms of C0, and let me solve for C3 in terms of C1, because in the end everything's going to be in terms of C0 and C1 anyway. So here I'm going to subtract this to the other side, and then subtract this to the other side and divide by 4. So C2 equals negative C0. It's a good start. Eventually everything's going to be in terms of C0 or C1. So C2 is now in terms of C0. For this one, same thing. Let me solve for C3 in terms of C1. I will subtract this way and divide by 4. So C3 is equal to 1 over 4. 3 over 12, that's 1 over 4, C1. This. Minus, because I subtracted that over. So what that means here is that I've got my C1 and my C3. Those are free variables. C1, C0 and C1, these are arbitrary, that is to say free coefficients. They can be whatever you want them to be. But then your C2 and your C3 are now known, at least in terms of C0 and C1. Okay. All right. But then you have C0, C1, C2, and C3. What about all the rest? Well, that comes from this power series. And because this power series is going to add up to 0, and because it's a power series, which means each individual term is independent, then if a bunch of independent terms that have no interaction all add up to 0, that's because each one of them was 0 in the beginning. And so I have another recursion. My recursion is going to be the equation c sub k times k squared minus 2k plus 4 plus c sub k plus 2 times 2 times k plus 2 times k plus 1. That whole coefficient times x to the power has to equal to 0. But since x is variable and can be literally anything, well then the thing that has to be 0 must be this. So this coefficient is 0. And that is our recursion. Our recursive algorithm. The best way to use a recursion, or I guess the most efficient way to use a recursion, is to not leave it in this form, but to solve for the one that has the bigger index. That way, once you know the smaller one, using that equation gives you the bigger one. So here, let me solve for ck plus 2. I will subtract this over to the other side. So this gives me ck plus 2 times all of this is equal to the negative of all of this stuff. So negative ck times k squared minus 2k plus 4. All right, so this is equal to the negative of this. Oh, but then I want just the ck plus 2, so I'll divide all of this stuff away. So over 2 times k plus 2 times k plus 1. Okay. And that's our recursion. They mean the same thing, but this one will be much easier to use just computationally. Note that to go from one to the other, there's a step of 2. That is to say, if to go from ck to ck plus 2, whatever k is, to get to k plus 2, you always take 2 steps. Which means that, unlike our previous problem, where we had them grouped into 3 columns, because there was a step of 3 from one to another, now the recursion will give you 2 columns, basically one dependent on your C0 and the other dependent on your C1. Okay, so that's the last thing. Let's go ahead and go through our recursion and see what we get. We don't need a C0 or a C1. Those are, as we mentioned, those are free variables. Those are allowed to be whatever they want to be. So let's go and take a look at all the rest. If I've got, oops, that's the wrong color. Right, okay, here we go. So if I've got C1, C2, C3, and C4 already from the end of my last page, I have C1 and C2 are arbitrary. We'll never find out what those are. We'll just leave them as C1, C2, C0, C1. We already know C2 and C3, so I guess the first one we really need is C4. Okay, so C4 is equal to, okay, well, for C4, we need this K to be the 2 right here. Okay, so that's going to be C2 plus 2. So that means all of these are going to be 2's. So that's going to be negative C2 times, oh, let's see, 2 squared is 4. 2 times 2 is 4. 4 minus 4 is 0. Plus 4 is 4. Over. Let's see. 2 plus 2 is 4. 4 times, 2 plus 2 is 4. 4 times 2 is 8. And then here 2 plus 1 is 3. And 8 times 3 is 24. So I end up with 4 over 24. You know what? Let me not write it that way. Let me write it this way. I'm just going to write it as 2 times. That's 2 plus 2 is 4. And then here I've got 2 plus 1 is 3. So I'm going to write it as 2 times 3 times 4. Okay, so I've got my negative c sub 2. That numerator worked out to be 4, and this denominator worked out to be 2 times 3 times 4. Okay, let's do C5. Oh, wait a minute. But then C2 can be written in terms of C0, right? C2 is the negative of C0. So if I come over here, the negative of C2 is C0. So that's going to be C0 over, and then the 4's cancel, and that's just 2 times 3. All right, very nice. Let's do C5. Okay, well then C5, the k is equal to 3 if I want this to be C5. So this would be negative C3 times 3 squared is 9. 9 minus 2 times 3. 9 minus 6 is 3. 3 plus 4 is 7. 7 over, and again I'm plugging in 3 here, so that's going to be a 2. If I plug in a 3, 3 plus 1 is 4, and then 3 plus 2 would be 5, like that. But then C3 itself depends on C1. C3 is negative a quarter of C1. So this would be negative 1/4 of C1. But then that's negative of a negative times 7 over 2 times 4 times 5. Like that. So here I end up with a double negative as a positive. Here a 4 times a 4 is a 4 squared. So I end up with C1 times 7 over 2 times 4 squared times 5. Ooh, I thought I was going to get a nice pattern like in the last one. It doesn't seem like I'm going to. Oh well. Let's see, C6. Well, in order to get C6, I need K to be 4. Okay, so 4 plus 2 would be 6. Okay, so that's going to be negative C4 times, okay, well now if I'm plugging in 4, 4 squared is 16, minus 8 is 8, plus 4 is 12, over 2 times 4 plus 1 is 5, and then 4 plus 2 is 6, like this. But then negative C4 is the negative of this thing right here. So this would be negative C0 over 2 times 3 times this 12, 2, 5, and 6. And here the 12 and the 6 and the 2 cancel. So I get negative C0 over, I'll keep writing it as 2, 3, and 5, but it doesn't look like I'm going to end up with any kind of nice pattern. Okay, so there we go. C6 is equal to negative C0 over 2 times 3 times 5. If I get what am I at, C7? Well then for C7 I need K to be 5. Okay, so that'll be negative C5 times, let's see, 25 minus 10 is 15. 15 plus 4 is 19. So that'll be 19 over, again, K is 5. So this will be 2, that'll be 6, and that'll be 7. 2 times 6 times 7. But in the last line, we learned that C5 was equal to this stuff. So now that's going to be the negative of this stuff, because I need negative C5, negative C1 times 7 over 2 times 4 squared times 5. And now that's being multiplied by your 19 over your 2, your 6, and your 7. And that is definitely not a nice pattern. Oh well. Let's see here. I've got... Oh, well, at least your 7s cancel. I guess that's something. Your 7s cancel. And then everything else stays the same. So that's going to be minus 19C1 over 2 squared, and then 4 squared, and then 5, and then 6. Okay. So that should be pretty good for now. So that means that, and of course you can keep going if you want to. It'll still just use the same algorithm. But that should be a pretty good substantial number of terms already, because now we get that y is equal to, by our initial assumption at the beginning of the problem, we assume that it's going to be this generic power series. It's going to be the sum, as n goes from 0 to infinity, of c sub n x to the n. Since you're centered at 0, it's just x to the n, not x minus something to the n, which is c0 plus c1x plus c2x squared plus c3x to the third plus c4x to the fourth plus ... But now we know those things. Again, C0 is a free value. We don't know what it is. We just leave it as C0. C1, same thing. We don't know what it is. We just leave it as C1. But then C2, from before, we had C2 was negative C0. Okay, so that's going to be negative C0 x squared. And then C3, that's our next one. C3 was negative 1/4 C1. So we get plus a negative 1/4 C1 x to the third. Okay, so that's C0, C1, C2, C3. Our next one is C4, which is going to be C0 over 6. So it's going to be 1/6 C0 x to the fourth. And then C5, that's going to be plus 7 over, let's see, 16 times 10, that's 160, x to the fifth. And then I need a C6, which is plus a negative 1 over, let's see, 6 times 5 is 30. 30x to the sixth power, plus, and I think I'm pretty good. I'm out of space here. Oh, sorry, I forgot my, this one had a C1 in it, and this one had a C0 in it. Let's do that. Let's just get that last one there. So C7, that's going to be negative 19 over 16, 64, and 64 times 30. That's 1920, is that right? 1920. X to the power 7 plus C1. And now, even though that looks like that's a single series, by taking all these coefficients and plopping them in the right place, C0, C1, C2, C3, C4, C5, C6, C7, by plopping those in the right place, I notice that every other term depends on either C0, like this, if I start with the first one, or they depend on C1, like these, starting from the second one. So I can separate those into two distinct linearly independent solutions. So in the end, my solution should be written as C0 times 1 minus x squared plus 1/6 x to the fourth. I've already factored out my C0. Minus 1 over 30 x to the sixth, and so forth and so on. Notice these are all just the odd powers. Plus, and then these all have a C1 in common, so I'll factor out a C1 times x minus 1/4 x to the third. And then the next one is plus, I already factored out the C1, so I just get 7 over 160 x to the fifth. And then plus a negative, so minus 19 over 1920. I've already factored out my C1, x to the seventh, plus ... And here we have an even function versus an odd function, so definitely linearly independent. And so our solution to this second order Cauchy-Euler equation is the linear combination of two linearly independent solutions, exactly as we would have expected since chapter 2, even if we didn't expect the solutions to be anything quite like this. So that's it for this question, and that's it for this topic. If anybody has any questions, please feel free to reach out, and I hope everyone has a nice day.